Welcome to this explainer. Today, we aren't just looking at the Colosseum as some beautiful static ruin. No, we are going to dissect it like an active, surviving machine. We're looking way past the gladiators to the absolutely brilliant, hidden engineering that allowed this ancient wonder to be built in the first place, and more importantly, why it hasn't fallen down.
Think about it for a second. It poses a genuine engineering paradox. How on earth can a stone building, standing over 50 meters tall, literally taller than the Statue of Liberty from base to torch, survive 2 millennia? We're talking about centuries of severe seismic activity, deliberate human demolition, and just relentless wear and tear. Statistically, it shouldn't still be standing, but here it is.
Okay, let's dive into this because here is the ultimate plot twist. You'd probably assume a building this incredibly heavy was built on solid bedrock, right? Well, it wasn't. The Colosseum was built on terrible, swampy, highly compressible ground. It actually sits right in a valley that used to be Emperor Nero's artificial pleasure lake. The Roman engineers surveying the site knew the soil was soft and waterlogged, and usually dropping a massive, rigid stone structure on top of a swamp guarantees uneven settling, massive cracks, and catastrophic collapse.
So, Chapter 1, The Mystery of Survival.
The first massive secret to the Colosseum survival is the sheer scale of its hidden foundation, because instead of pouring a flat, standard concrete slab, the Romans dug down, deep. They constructed an enormous elliptical underground ring of concrete that's 12 meters deep and 12 meters thick. That is almost 40 feet of solid, unbroken structure, perfectly following the perimeter of the outer wall.
So, what does this all mean? Well, this unseen concrete ring brilliantly bypasses that soft alluvial swamp soil completely. By digging down 12 meters, they hit firm, load-bearing ground. The entire weight of the Colosseum, and we're talking roughly 100,000 cubic tons of heavy travertine stone just in the outer walls alone, is concentrated directly over this ring. It safely transfers all that immense weight right through the soft earth and down to the stable substratum far beneath it. Literally a masterclass in foundation engineering.
Moving on to Chapter 2, The Efficiency of the Ellipse.
And this brilliantly illustrates exactly why the building's overall shape is absolutely crucial. Zooming out to the macro level, we can see why the Colosseum isn't a perfect circle. Now, an ellipse does create 2 focal points, giving 50,000 spectators optimal sightlines. It also allows for distinct ceremonial axes, like the Gate of Life and the Gate of Death. But the real masterstroke here is structural. You see, an elliptical form distributes its massive load around its perimeter much more evenly than a rectangular building ever could. A rectangle has corners, and corners are exactly where structural stress concentrates and fractures happen. The continuous sweeping curve of the ellipse actively prevents these localized stress points, making the entire building incredibly resistant to collapse. Chapter 3, the vault system. So how exactly does the Colosseum manage its own massive weight dynamically? Well, the answer lies in its modular radial vaults. The interior isn't just one big solid mound of rock. It's an intricate system of vaulted corridors made entirely of concrete and brick, and these act as independent wedge-shaped modules. Think of it like a giant puzzle. This means that if a massive earthquake strikes and severely damages one section of seating, that localized failure doesn't pull down the adjacent sections with it. It is a brilliant, compartmentalized design that completely stops the domino effect of destruction right in its tracks.
There's a totally fascinating historical irony here, too. When you look at the Colosseum today, a huge chunk of the iconic outer wall is just gone, famously destroyed by an earthquake back in 1349. Now, we tend to think of that beautiful outer wall as the main building, but actually, it was essentially just a decorative, rigid facade. The inner vaults, those hidden modular corridors where the crowds actually walked, are the true, resilient, load-bearing skeleton. They are what kept the building standing, while the beautiful outer skin literally fell away.
Chapter 4, The Secret of Roman Concrete.
If we zoom in to the microscopic level, we meet Opus Caementicium, Roman concrete. This was the ultimate enabling technology of Roman monumental architecture. Honestly, without this specific, precise mixture of lime, volcanic pozzolana ash from the Naples region, water, and aggregate chunks, the Colosseum simply could not exist. This ancient magical material is what allowed them to pour those massive vaults spanning huge distances without instantly crumbling under their own weight. But they didn't just pour the exact same concrete everywhere. The engineers dynamically altered the chemistry of the building as it rose higher and higher.
Down in the lower foundations, they mix the concrete with heavy, dense tufa stone and brick for maximum compressive strength. But as they built the upper vaults of the seating area, they completely switched the aggregate to pumice, which is a really light, airy volcanic glass. This strategic genius drastically reduced the top-heavy strain on the structure. They essentially made the building lighter the higher up it went.
So the crucial point is this absolute marvel of ancient chemistry. Modern concrete degrades over time. It cracks, water gets in, steel rebar rusts, and it generally falls apart in about a century. But the volcanic pozzolana ash used by the Romans actually causes their concrete to gain strength over millennia. You heard that right. As groundwater seeps through it over the centuries, the volcanic minerals continue to chemically react and crystallize within the concrete matrix. It constantly binds and heals the material from the inside out. It actively defies normal decay.
Chapter 5: A Legacy of Stone. When you combine those brilliant deep foundations, the load distribution of the ellipse, modular vaults, and self-healing concrete, you get an absolute architectural miracle built in just 8 years. 8 years! That is astonishing even by today's standards. After excavating the foundation, the Romans didn't have to build sequentially. Because of that modular vault design we talked about, they used parallel construction. Multiple teams of specialized laborers poured walls and vaults and installed seating simultaneously, working on different wedge-shaped sections all at once.
And so it still stands. As the 8th century monk, the Venerable Bede wrote, "While the Colosseum stands, Rome shall stand." It survives today not just as a picturesque ruin for tourists, but as an eternal testament to the anonymous hands that mixed its concrete, calculated its elliptical loads, and carved its stone. It is a masterclass of engineering that just refuses to die. I want to leave you with this final, provocative thought. We pride ourselves on our towering modern skyscrapers of steel and glass, all designed with supercomputers. But how many of our buildings will survive a swampy foundation, massive earthquakes, and 2 millennia of weather? What modern buildings will have stones that remember us in 2,000 years? It really makes you appreciate the hidden systems of history, doesn't it? Thank you so much for joining me on this explainer, and keep questioning the incredible structures all around us.